Hello all of you. Welcome to the 46th lecture on the course on analysis and modeling in chemical engineering. In this week, we will discuss about separation processes and how we can model that. And then in the following week, we will discuss what is known as the mesh equations, which is typically applied to separation processes. So before I go further, I want to begin with some basics of separation in today's lecture, and then we will come to the idea of cascades and all that, which we will model in the following lectures. So one thing that is very important to understand as chemical engineers is we are not only interested in the chemical reactions. One of our main job, apart from performing the chemical reactions at large scale, is also to perform separations, because in the end, whatever chemical reactions do happen in a chemical reactor or for other processes as well where there is no chemical reaction, there is a great need for separation process to ensure the purity of the product as required. And if you look at the separation process, there are many aspects that one has to consider. The very first aspect is how can we separate two components in a mixture, let's say, and we have to basically identify what are the properties that we can manifest or harness in order to separate two things. You should have a substantial difference in that property of the two component. For example, in the distillation column, we are looking at the boiling point. The boiling point are substantially different for the two components, and therefore we are able to separate that. If, for example, the boiling point is similar, therefore we cannot do distillation for that component, right? And then once we choose a particular separation process, we need to see like how we can make it more efficient, for example by using multiple stages or cascades, as we will discuss in this in the coming lectures. Okay, so the general separation process therefore is basically something like this. You have a process, black box, that gets some feed which can be in any phase, liquid or vapor, and then we either supply energy separating agent, let's say the heat in the case of distillation, which is referred as ESA, or we supply some mass separating agent, for example the absorbent, that basically absorbs one of the components selectively from the mixture, right? And no matter what we do, we end up getting basically a number of product streams from there. For the binary distillation, we have two streams, one from top, one from bottom. But in general, let's say a fractional distillation or a general separation process may have n product streams coming out. And then if I'll have to look at the general mole balance, it is something like this, where for every component going from I equal to 1 to C, I can do a mole balance, assuming that there is no chemical reaction taking place inside the separation process. We can basically perform a mole balance like this, that is, whatever number of moles are coming in the feed stream, that should be equal to the sum of the number of moles coming in the product streams, which are represented by NIP, right? So in all the cases we will discuss in this course, we assume that there is no chemical reaction taking place inside the separator, but there are cases such as reactive distillation where the reaction occurs along with separation in a column, right? So we will not discuss those cases. We will confine ourselves to cases where there is no chemical reaction taking place, just for the sake of simplicity, and also it is most common if you think about it. Okay, so as I said, in order to separate two components of a mixture, we need to basically exploit difference in some property of the components in the mixture, and it typically involves either a creation of a phase or addition of a phase, right? So let's say, for example, I give an example of distillation. So we are supplying an energy separating agent, which is heat, and it leads to the creation of a new phase in distillation. Addition is, let's say I add an MSA and one of the components get absorbed in the mass separating agent MSA, and here the separation is happening by the phase addition, right? So I'm giving some examples here. For example, if the property of interest is the boiling point or the relative volatility, in that case we can use basically heat, that is ESA, energy separating agent, and here we have phase creation. In fact, evaporation, which we have discussed earlier, also falls in this category, but there one component was completely assumed to be non-volatile. So, therefore, we can get 100% separation, so as to speak. Distillation is a more general situation where both components, or if there are multiple components, then multiple components can all be volatile, but then they differ in their relative volatility, and therefore, we can separate them on the basis of their boiling point. The other property that one can harness is solubility, and here we basically are doing a phase addition. Typically, we add an MSA, and the example of that is, let's say, a liquid extraction. So, you have a liquid mixture containing, let's say, two component, and you pass another liquid containing a third component C, and let us say A is soluble in C and B is not, or if A is more soluble in C and B is less soluble in C, then what is going to happen eventually is that the A will tend to go with C and the B will remain in the other liquid. So, in this case, basically B is going from one phase to the other, and the other phase is the one that I have added. C is my mass separating agent, and A and B are basically components of my mixture. We can also do an absorption process where the idea is something similar, but where we have some kind of an absorbent where one of the components get absorbed as opposed to plain diffusion. Let us say if you have a liquid absorbent that is getting added. So, that is also one possibility. It is quite similar to solubility to some extent, but there are differences that we can discuss. Here also we are adding a phase, and here also we are adding an MSA, which is an absorbent, and there can be essentially two processes here. Typically, when we use absorption process, we are not referring to just two liquid phases, we are referring to one liquid phase and one vapor phase. That is the fundamental difference compared to the liquid extraction, or LLE, so as to speak. In this case, we have a vapor phase and a liquid phase, and now if the liquid phase is my absorbent, then in that case I will use the term absorption. Then the liquid phase basically absorbs things from the vapor phase containing two components. So, the vapor phase therefore contains two components A, B, and liquid may contain an MSA C. If that is happening, this is my absorption process. Stripping, on the other hand, is opposite of that, where the vapor phase contains the MSA and the liquid phase contains the mixture AB, and basically vapor takes away the one of the components from the liquid mixture, right. That is the fundamental difference here between absorption and stripping. We can also have something like an adsorptivity when we are using a solid absorbent. Here again we are adding a phase which is a solid phase containing the adsorbent, and here again we have an MSA and we are basically separating by the adsorption process. There can be other things where a phase addition or creation is not required. For example, there can be separations based on the size of the molecules or their permeability. For example, the membrane separation, where the membrane selectively allows one of the components to pass through. For example, in the case of osmosis or reverse osmosis. So, there the separation is purely because of the size and permeability. Or we can also separate in response to some electric field. There we are using some kind of an ESA. Let us say I am using an electric field to separate two components of the mixture, one component which is relatively more charged, that gets separated using that electric field, right. We can also think about the separation by using gravity or centrifugal force and things like that, where the separation is purely driven by a force field. It is an external agency and there is no phase addition or creation required as such in the last two cases which we discussed. So here are some examples where we are doing separation by phase creation. The first example we have discussed already earlier, where we can have a liquid feed. In general, you can also have a vapor feed, but most cases you have a liquid feed because you want to concentrate that liquid. So you have a liquid feed and you are basically heating it up and you are getting a vapor product from top and liquid product from the bottom. And in this case, there is a complete separation of the component in the vapor and the liquid, right? So one component, it really goes in the vapor, the other component remains in the liquid. Let's say in the case of a sugar solution, the vapor does not contain any sugar, all the sugar goes in the liquid phase, right? Or for the case of a seawater evaporation, all the salt remains in the liquid phase and the vapor contains the pure water. Okay, so this is the case of evaporation. You can also have a partial vaporization where the evaporation is not complete, right? And in that case, you can have, for example, a vapor or a liquid input, and there is a partial vaporization. It is not a complete separation by evaporation, but again, we are forming a vapor phase and a liquid phase. The difference is that we are not completely able to separate the component. It is not that one component is completely non-volatile, right? Then in general, we can have a distillation process that is basically an extension to the partial vaporization idea, where we may also like to condense the vapor product to get a liquid product, and we still have a liquid product, and we can supply additional heat as required, and we can have a vapor or a liquid feed stream. We can also have a flash evaporation that is quite similar to the evaporation. The only difference is that in the case of flash evaporation, the evaporation is basically triggered by lowering of the pressure of the liquid. As we lower the pressure, the boiling point reduces and therefore vaporization takes place. And if that is the mechanism being used here, then in that case we call it a flash evaporation, because this example of this kind of a process is this process is an example of a flash process. Then finally we can have something like crystallization, where again you can have a liquid feed that is kind of separated into a vapor, but also a solid product, that is a crystalline product, again by using heat. We can also look at examples of separation where we are doing a phase addition. As I was discussing, there is an example of absorption where we are supplying a vapor feed. From the vapor, I want to separate a component. So we supply a liquid MSA from top that falls down the line, and the liquid goes away with that component which I want to absorb from the vapor. The stripping is opposite of that, where the MSA is now a vapor and the feed is now a liquid. So vapor goes up and carries one of the component of the liquid. We can have a liquid-liquid extraction where essentially you have a liquid feed, let's say L1 coming in, and we supply a MSA that is also a liquid. So that liquid basically carries one of the component in the L2 stream, and whatever is going up, that is another stream L1. Keep in mind that up and down is just shown for representation. It will depend on the density of the two liquids, but the general idea is that we are using a liquid MSA to separate a liquid component from a liquid mixture. There is also something called a leaching process, where we have a solid feed containing a soluble component and an insoluble component in the MSA, that is a liquid, and we pass this MSA, it dissolves the liquid in the soluble component of the solid, and it basically carries the liquid containing the soluble component, and the solid product coming out, it contains primarily the insoluble component, right? The best example of a leaching process is when we make tea. So when we first, let's say, add tea in hot water, the tea actually contains basically a soluble component and an insoluble component. The soluble component basically goes away in the hot water that give rise to the distinct color of the tea, and the insoluble component remains in the tea leaves, which have to be filtered out, right? That's the fundamental idea that is going there. That is an example of leaching process. Okay. So, as you may expect, that separation is going to demand energy, and in fact, when we were doing this evaporation processes, we have found that if we are using multiple effects, that in in principle is more effective, because in the case of evaporator, let us say I can use the fresh steam only in the first effect, and whatever vapor that is coming in from there, that can become the heating medium of the subsequent effect. In a similar manner, the separation processes in general may be done in a sequence of stages that can be helpful in many ways. One of the ways is, let's say, the the mixture contains multiple components. In this case, let's say it contains some C3 product containing 3 carbons, IC4 product containing 4 carbons, NC4 again containing 4 carbons, and then IC5 and NC5 product. Let us say these are the 5 products which I want to separate as much as possible. So, you see, in the first stage the C3 comes out, then the remaining is everything else that is going in here, which is IC4, then NC4, then IC5, then NC5, all of them gets there. In second stage, IC4 comes out as a product, and the remaining thing is now NC4, IC5 and NC5, and out of that NC4 is coming out in the third stage, and IC5 and NC5 basically comes out from bottom together as a mixture, right? How we are able to achieve that? We can achieve that by working with, let's say, different boiling points. For example, let us say the operating temperature here is T1, here is T2, and here is T3, and let us say T3 is higher than T2, higher than T1. Then C3, if it has the lowest boiling point in the mixture, C3 only can boil at T1 temperature, let us say. Then the first stage can operate at a lower temperature T1, where only the C3 can evaporate. Then once it gets to second stage T2, now we have C3 is not there. So, now out of the remaining components, IC4, let's say, is the having a lowest boiling point, that is at T2, let's say. So, IC4 can come out in the second stage, and then the remaining gets to the third stage, and let's say NC4 now has the least boiling point and it is equal to T3, then in that case NC4 can come out in the third stage. So, that is how we can basically manifest the differences in the boiling point to create a sequence of stages. It may not always be something like the energy requirement, which for example we had in the case of evaporator. It can also be the requirement because of the separation we want to achieve, because we have a mixture containing many components and we want to separate all of that. So, therefore, we may choose to have a sequence of stages, right. Now, once we have that, then there are of course many possibilities in which that sequence can be created, which can give you essentially the same 4 products, right. I can, for example, do like this or like that or like that. So, they are differing in the way in which the components are getting separated, right, and how the columns are positioned to each other, right. So, the number of such possibilities therefore basically increases with the number of components that we have in the mixture. And now, of course, it is also now a matter of choice of which of those sequences should we pick. Of course, we have to look at the energy requirements and all that, and to decide on which of these sequences can be the most optimal sequence. But before we do that, we have to enumerate all the possible sequences, right. So, for example, if I have only 2 products and I am using, let us say, a binary column, then in that case the feed can be separated in a single column right here. So, I need only one sequence, only one possible sequence is there. because the feed gets separated right there, right? Of course, you can say that the P2 comes from top and P1 at the bottom, but top and bottom has no meaning here because both of them are basically able to separate the two products, right? However, if I have, let us say, three products which I want to get out, now there are two possibilities. Now, the first possibility is the feed comes here. One product comes out from the first stage top, and the bottom product of the first column is becoming the feed for the second column, and the other two products come from the second column, right? I can do kind of opposite of that, where instead of taking the product from the top in the first column, I can take out the product from the bottom, and the top product becomes now the feed for the second column, right? In the previous example, I said that top and bottom doesn't matter because we are able to separate two products out anyway, P1 and P2. But now in this case, it does matter because this process where, let us say, if you have a vapor liquid thing and the top product may contain the vapor, the bottom may contain the liquid. So depending on which sequence I am choosing, the feed is changing to the second column. In this case, it may most likely have a liquid feed, and in the other case, it may most likely have the vapor feed, right? So for intermediate columns, we have to differentiate between the product coming out from the top column or the bottom column, because that the other part is becoming the feed for the subsequent column that we are having. Let's say in here, this is column 1, this is column 2. So the bottom product becomes the feed here, and in this case, this is 1, this is 2. The top product becomes the feed there. So we can extend this idea, and now let us say we have 4 products and we have to figure out what all different sequences we can have in that scenario. So let us try to draw it. So now clearly I need more than 2 columns, because using one column I can separate 2 products. Using 2 columns I can separate 3, as we have seen, and using 3 columns I can now separate 4 products, right? So one possibility is this, that P1 comes out of this and P2 comes out from the second column, and P3 and P4 comes out from the third column. And now P3 and P4 I can interchange, that doesn't matter. But what is important is that this feed is coming from the bottom. These feeds to the second and third column comes from the bottom stream of the first and second column here, right? So now I can of course change that, and I can have something like this, where from the first column, the top part becomes the feed for the second column, and the product P1 comes from the bottom of the first column, and the P2 is still comes from the top of the second column, and P3 and P4 are as earlier. Or I can do something like this, where the feed comes the first column as usual, and this still comes from the top, but then I basically take the product from second column from the bottom, and P3 and P4 are as earlier. Or I can also do something like this. right? So now there are 4 possibilities that we have done. There is also a 5th possibility where the first column does not give any final product. Instead, the top product goes to one column and that gives 2 product, P1 and P2, and the bottom product of first column goes to another column that gives me 2 products, P3 and P4, right? So now we have 4 products and there are 5 sequences of 3 columns. So as you can imagine, as we increase basically the number of products to take out from a mixture, you need to basically introduce more columns, and there are now many possibilities that will emerge for the sequence in which you can arrange them, right? In the next class, I will take an example where I will think of this as some sort of a graph or a tree. Okay. So one concept which we have introduced in the earlier lectures when we discussed the fundamentals of chemical engineering was the idea of this phase equilibrium for a multi-phase, multi-component system. As we have discussed, typically the separation processes involve a phase creation or the addition. So the typical situation is that we will have multi-phase conditions inside the separation process. No matter what the separation process is, it will be typically in a multi-phase situation. It can be a 2 liquids, it can be liquid and vapor, it can be liquid and solid or whatever. The main point is that it is going to be some kind of a multi-phase condition. And of course, since it's separation process, we want to separate something out of a mixture. So by default, it has to be a multi-component system. And it helps to assume that the condition inside the separator is essentially of some kind of phase equilibrium. That essentially means 3 different conditions. The first condition is of thermal equilibrium. That means temperatures of all the phases are the same. The second condition is that of mechanical equilibrium, that says that the pressures of all the phases are also same. And the third condition, that is the most important condition, is the phase equilibrium condition, that says that the chemical potential of every component in all the phases are also equal, right? So for components I going from 1 to C, the chemical potential of I in the phase 1 is equal to the chemical potential of I in the phase 2, and that is equal to chemical potential of I in the phase P. And finally, we have discussed that for chemical potentials, we need to have some sort of a relation coming from an equation of state. In general, the chemical potential depends on the composition, the temperature, and the pressure. And finally, for every phase, we also have a condition for the summation of the mole fractions. The mole fractions must sum to 1 in each of these phases. So based on these conditions, we have derived what is known as this Gibbs phase rule for a multi-phase, multi-component, non-reactive system, considering only the intensive variables first. These are the quantities that depend only, they do not depend on the quantity. For example, the temperature, pressure, and chemical potential, they don't depend on the quantity, and therefore these are intensive variables. So only for those variables we can find the degree of freedom as something like C minus P plus 2, where C is the number of components, P is the number of phases, right? And we have done some examples, applications of this. How did we get this relation? We basically counted the number of equations that we have, and we looked at the number of variables that we have. The number of variables minus the number of equations gave me the degree of freedom. So that's what I am showing here. So we have, for example, this separation process where a feed at some condition, the feed condition Tf, pressure Pf, and some enthalpy is getting separated into a vapor phase and a liquid phase, and we get a vapor product, a liquid product, right? What is important here, that the feed itself can be in any condition, right? But the conditions inside the separator, whatever vapor condition that we have inside the separator and the liquid condition, that is same as the vapor outlet and liquid outlet respectively, right? So, just like what we had for the case of a CSTR for chemical reaction, that the concentration inside the CSTR was the same as the concentration at the exit. In a similar manner here, the vapor phase composition and temperature and pressure will be the same inside the separator and in the stream going out, but it can be different in the feed stream. And same is true for the liquid phase. The conditions inside the separator and in the outlet stream are going to be the same, but the feed stream of course can be different. In fact, the feed can be any arbitrary mixture of a liquid and vapor, or it can be pure liquid or a pure vapor, doesn't really matter. So, all the equations therefore we write, particularly for the intensive variables, are only for inside the separator, assuming the condition of phase equilibrium. That means the temperature equality, pressure equality, chemical potential equality, and of course property relations and the summation of mole fraction equations. By definition, we use xi for the liquid phase mole fraction and yi for the vapor phase mole fraction. And therefore, we can count the number of variables that we have, the number of equations that we have. You can go back at the detailed derivation we have done earlier, and we can basically derive the Gibbs phase rule in this way. We can also consider all the variables, and in that case we have some extra equations. We have a material balance equation, we have an energy balance equation, and now we have the enthalpies that has to come from the equation of state. We have a summation of mole fraction equation for the feed condition, and again we have some new variables also coming in there that has to be taken up, let's say the heat supplied and so on. And finally, we can get the degree of freedom. If I also consider the extensive variables, it is going to be something like C plus 4, and this also we have derived earlier. So, one thing that is typically used in separation process literature or chemical engineering literature is that instead of chemical potential, sometimes it is more convenient to work in terms of a quantity known as fugacity, right? Fugacity, you can imagine, is something like pressure. It has units of pressure. In fact, for an ideal gas, the fugacity is equal to the pressure, but for non-ideal gases, the fugacity may depart from the pressure. It is some kind of a real pressure that you have in the system, or the pressure felt by the other components in the mixture because of the presence of one of the component, right? So, although it has a unit of pressure, it is not the same as the absolute pressure, except in the case of an ideal gas, right? For an ideal gas mixture, the fugacity is given as basically same as the partial pressure, the pressure multiplied by the vapor fraction, vapor mole fraction. And based on this condition for this ideal gas and ideal gas mixture, we can now define something known as the fugacity coefficient, which is for a pure substance is equal to the ratio of the fugacity Fi by the pressure, and for a species I in a mixture, that is going to be something like Fi bar by YIP, Fi bar by YIP, where this Fi bar, the partial fugacity, is related to the chemical potential by a relation like this, where C is some arbitrary constant, mu I is the chemical potential of a species I, and T is the temperature, and R is the gas constant, right. So, basically, instead of writing, now let us say mu I L is equal to mu I V, since Fi is something like this, I can also, since these two are equal for the same condition of temperature and pressure, because temperature is anyway same at equilibrium in the two phases, we can also write it as C exponential mu I L by RTL is equal to C exponential mu IV by RTV, because TL is also equal to TV. So, if this is true, this also has to be true. What this means is that the condition for the phase equilibrium can also be expressed in terms of the partial fugacities FIL equal to FIV. And once we have written in terms of partial fugacity, we can also define it in terms of partial fugacity coefficients, as we will do next. So, you see, we can define a partial fugacity coefficient for the vapor and also for the liquid. As I have just said, for ideal gas mixture, the fugacity is given as P into Yi. So, therefore, the partial fugacity coefficient becomes equal to 1. But in general, for a non-ideal mixture or any real mixture, this partial fugacity coefficient will not be equal to 1. If we use the condition of an ideal solution, in that case, for the liquid phase, I can write a relation like this, where the pressure inside the liquid can be assumed to be something related to the saturation pressure of the or the vapor pressure of the pure component I. And if I use this relation, I can get the relation for the partial fugacity coefficient as something like PIS by P, right? So, if I use this language just to somewhat complicate our earlier language what we had in terms of chemical potential, but something which is more standard in chemical engineering. Basically, this amounts to writing this chemical potential equality as the equality of the partial fugacities. And since the partial fugacities can be expressed in terms of the partial fugacity coefficients, we can have a similar relation in terms of partial fugacity coefficients, where we have got an extra factor YIP coming from the definition of partial fugacity coefficient for the vapor, and extra XIP, the same thing for the liquid. So, by doing that, we can get something like a quantity Ki, that is the ratio of the vapor phase mole fraction Yi and the liquid phase mole fraction Xi in terms of the partial fugacity coefficient of the liquid and the partial fugacity coefficient of the vapor, which has to come from the equation of state. So, it is a shortcut way of writing it, but keep in mind that this particular quantity has to come from the equation of state. So, long story short, it basically helps us write our equation in a simplified notation as something like this, where this Ki, which we can call as the K value, will have to come from thermodynamics. It is essentially a ratio of the partial fugacity coefficients of the liquid and vapor, which in turn depends on or is a function of the partial fugacities, which in turn can be expressed in terms of chemical potential. So, essentially, this is another way of writing the phase equilibrium condition that says that the chemical potentials are equal. We can also express that in the notation like this, where the K contains all the thermodynamic information that is there in the system. In the case of liquids, it is sometimes convenient to work in terms of what is known as activity of a component I in a mixture. The activity of a component is defined as the ratio of the partial fugacity with fugacity of the pure component at the same pressure and temperature and phase as the mixture, as the same pressure and phase as the mixture, right. This is what is referred as a standard state. This activity, just like fugacity, gives a sense of pressure, that is what I want for the gases typically. Activity gives a feel of something like a mole fraction. And for an ideal solution, the activity essentially equals the mole fractions, right. Now, just like we have defined the partial fugacity coefficient, we can now define something known as the activity coefficient, that is the ratio of the activity with the mole fraction. Again, for the ideal solution, the activity coefficient will become 1. And now, I can write the equality of the partial fugacities as the equality of the corresponding activities. by this relation, and that basically gives me a relation in terms of the activity coefficients, and therefore we can essentially get something like, again, a relation for the k value, the ki, that's the ratio of yi to xi, and that can be expressed as the ratio of the activity coefficients for the components, right? So many a times in literature, for the gases, the thermodynamic relations are given in terms of the partial fugacity coefficients, and therefore this language becomes convenient for the case of gases or vapors. And for the case of liquid, the same is typically expressed in terms of activity coefficient. So therefore this becomes important. But the key idea is that this ki is essentially coming from thermodynamics, and essentially it comes from the same condition of phase equilibrium that we have discussed, but written in a somewhat complicated manner. So with that, I conclude this lecture. In the next lecture, we will talk further on this idea of k values, and we will see how exactly this helps us in the modeling of separation processes. So with that, I conclude here. Thank you so much.